Now, oxalate will bind at each of these oxygens. So in every oxalate molecule, it will bind once there, it will bind once here. And if we have our metal that's in the middle, we get a binding happening there and there. That is not two oxalate molecules, but that's just one, which means if we had two, like in our little guy over there, drawing the second one here, draw them upside down. The two oxygens in the second oxalate molecule, this oxygen and this oxygen, will also come in and bind here and here. And now if we look at it, we can see that 1, 2, 3, 4 atoms are actually attached in this situation. So the coordination number here would not be 2, it would actually be 4 in this particular case. Any questions on that there? So again, there are some ligands that combine in a lot of places, something like EDTA, ethyl-diamine tetraacetic acid, actually combined in 6 places per one molecule. So it increases the coordination number. And again, we'll talk more about this in a later chapter, but again, sometimes people fall into the, well, it's got to be the number that's on the bottom would be the coordination number. And it's not always, again, because it has the ability to sort of bind in some different places, are 2 per molecule or 3 per molecule or 6 per molecule. You may end up with some different coordination numbers you may not anticipate. One thing though about the ligand is it does attach, or it's added basically one at a time. So very much like when we add, very much like when we lose an H plus off of a diprotic acid or triprotic acid, they basically come off one at a time. So same idea here, the ligands basically come on one at a time. So for example, earlier on the last page, we saw the overall reaction here for this guy here. And we see we have 4 ligands here that are attaching. And this overall reaction implies that all 4 of them maybe pop on all at once. And it actually doesn't occur that way. It occurs in a stepwise fashion. So just to kind of show you with that example, what's happening when those ligands are attached. The very first thing that would happen is the cobalt there would pick up basically one ligand here, one chloride. And it basically would attach as COCl. Now what we would have actually is a plus in terms of our charge. +2 and -1 is +1. There would be an equilibrium sort of constant and expression for what's happening here. The next thing that would happen is our COCl plus would pick up another chloride. And we will end up with COCl2. That also would have an equilibrium sort of value expressed with it. The third step that would happen is the third chloride would come on to this guy, again, continuously adding to the same thing, giving us COCl3, and now we become minus, and there would be an equilibrium expression for that guy as well. Finally, our fourth guy would come on. Giving us COCl4 2 minus. And that gives us a fourth equilibrium one. This is what is sometimes referred to as a stepwise sort of adding. So these ligands do come on basically one at a time. Now you may be wondering, how do we go from that to that overall reaction? We actually do it exactly like we talked about with regular equilibrium guys. We're going to add these reactions together. When we add these reactions together, again, anything that's on opposite sides of the arrow, that's the same, can cancel or reduce. That means this guy and this guy cancels. That means this guy and this guy cancels. That means this guy and this guy will cancel. That leaves us on our left-hand side of the arrow, our cobalt plus our 1, 2, 3, and 4 chlorides that are going to come together. And going to make our complex ion here. So again, we sometimes focus on the overall reaction, but again, it's important to remember that these things do come on basically one at a time. How would we get the Kf for this reaction? So the Kf for the overall reaction, basically we added all these equilibrium reactions together. Remember that when you add equilibrium reactions together, you basically multiply the K values. So this will be K1 times K2 times K3 times K4. And that would give you your overall K value in this particular case. Any questions on that there? Okay, so this is a little bit about complex ions and sort of the equilibrium that goes with it. Actually, when we do these problems, we actually do some different sort of ways that we sort of tackle these problems. So let's take a look at an example here to sort of finish up lecture here. Let's take a look at this example together and talk about some of the things that are kind of similar to what we typically do and some of the things that are a little bit different in terms of what we do here. In this particular problem, we're going to assume that the total volume of everything is 1 liter. We don't always do that. We're just going to do it in this particular example here. So we basically have this complex ion that's formed from the reaction of copper plus 4 of these really good ligands, which is NH3, making our complex ion over here, our tetraamine copper 2 ion here. And we have our Kf value, that's 5 times 10 to the 13. So let us see how we would go through this sort of table here and this reaction. The first thing that we would want to do is we would want to do an ice table. And we would want to get the concentration of everybody in the solution. So again, we're going to assume in this particular example, everything is 1 liter. So that means that we have 0.2 molar copper 2 sulfate. The copper 2 sulfate is pretty much the only source of copper that we have in here. And that means that our initial guy here would be 0.2 molar. Again, this being the only source basically of copper. We have a liter of 1.2 molar NH3. So our concentration of NH3 in this case is 1.2 molar. And we're going to assume 0. That's going to happen here. Now, a very big assumption that we do in these sort of problems is we look at the Kf value and we see it is 5 times 10 to the 13. That is a very large value. What that means is that's a very large value of K. If you think about large value of K is like above 1, so that's like 5 times 10 to 13. That's very large. That even though this thing is technically a reversible reaction, it is pretty much 100% heading in this direction. Again, even though technically speaking, it is reversible, it is pretty much 100% heading over there to making that complex ion. What does that mean for our metal? Well, it means that in these cases, we assume that all of the metal will get used up. In the complex ion. And again, it's because this value is so large that we're going to assume the metal, which is in the center of the complex ions, kind of like the limiting reagent, is going to get used up pretty much 100%. And what that means for our table is we already know what the change will be. The change will actually be, in this case, the amount of the metal, which is the copper. So it'll be minus 0.2. We also know over here it'll be minus 4 times 0.2, and this will be plus 0.2. Now you may be wondering, like, what's the deal with all the numbers and stuff like that? Well, if we did a regular ice table here, we would have started with 0.2, 1.2, and 0. And if we use x, this would be minus x, this would be minus 4x, and this would be plus x. And that's essentially what we just did here. This is minus x, this is minus 4x, and this is plus x, right? We just happen to know what x is at this point. X is 0.2, which is the metals concentration. So we kind of already know that number, and that's why we just put it in. Again, it's important to make sure that you do the stoichiometry part. So that's why the 4 is there again. Otherwise, you will end up with the wrong answer. Any questions on that there? I'm just going to get rid of this so it's not so messy here. Okay, so that means at this point, if we bring everybody down, we would expect all of our copper to be gone. We would have 1.2 minus 4 times 0.2, going to give us 0.4 for this guy, and 0.2 for this guy. At the end of this table, we actually have the concentration at equilibrium of NH3. So the concentration of NH3 at equilibrium would be 0.4 molar. We also have the concentration of our complex ion at equilibrium. It would be 0.2 molar. Now, you may be wondering, that's good, but aren't we looking for the concentration of copper? And you would be right, and you go, is the answer 0? And the answer is no, it would not be 0. Otherwise, we wouldn't be doing these type of problems because every answer would end up being 0. And really the reason why it is not 0 is because even though this is a very large value of K, and we're assuming that pretty much 100% of everybody is going to the right, it is still an equilibrium reaction, which means even though it's almost pushed 100% of the way to the right, there is still a little bit of it that wants to go back this way. And a little bit of that complex ion will break apart into the copper ion and the ammonia ion, which means we will have a little bit of it left at equilibrium. So what that means is the second part of our assumption is, even though that most of it is in the complex ion, because it's still a equilibrium reaction, a little of the metal, free metal ion, will be in solution. And what is our second assumption? Our second assumption is it should be a very small number for the metal ion. So a really, really small metal number there for its concentration. So how can we get to solving for that? Well, even though we zeroed it out in our original ice table, we're going to go back now and call it X because we're going to go look for it. And how is that going to help us? Well, we have the equilibrium concentration of this guy, we have the equilibrium concentration of this guy, and we have the Kf value. So we could actually now use the Kf expression here to help us really solve for it. And again, you don't want to forget to make that to the 4th in this case because of the coefficient. And that would equal 5 times 10 to the 13. Putting in our numbers, we have 0.2 for our complex ion. The copper is what we're looking for. And we have 0.4 for our NH3. Again, we want to cube it. That's going to be 5 times 10 to the 13. By the way, mathematically, these guys switch places. when you rearrange that equation. And if you do, you end up with a copper concentration that is equal to 0.2 divided by 5 times 10 to the 13 times 0.4 to the 4th here. All right, putting all those numbers in, 0.2 divided by 5 to the 13 divided by 0.4 to the 4th. Going to give us a copper concentration of 1.6 times 10 to the minus 13 molar. So let us think about that number and what it means, and does it validate our assumption? Our assumption was, first off, that all of the copper is going to be tied up in that complex ion because the K value is so large. And even though all of it's going to be tied up in that complex ion, because it's an equilibrium constant or reaction, some of it will come back and break apart. But what we should have in terms of free copper in this case should be a very, very small number. I would classify that as a very, very small number. That's 12 zeros in front of that one. And that's essentially zero, if you will. Even though there is, this smidge of free copper ion floating around, super small amount. There's still a little bit of it there, but pretty much, I would say 99.9999% of it is pretty much hanging out in that complex ion. And that's because the formation of complex ion is extremely favored because of the Kf value. Any questions on that calculation there? So again, here we did get a very small number, which again does sort of validate our thoughts. Any questions on that there? Okay, we will